Hey everybody, this is an extra video for Electrical Engineering 235, and the main point of this video is to help you to understand how to do problem 32.3. In other words, that's problem 3 on test 32. But really, what I hope to do in this lecture is to show you the entire design sequence. And I hope that you'll find this interesting. I think that you will possibly be really interested and impressed with how much you know how to do. So what it is that we want to do in this lecture is to design a synchronous state machine to detect the sequence 0, 1, 1. And then we will test it on the sequence that's shown there. Now just think about this for a moment. If you had been challenged with designing something to detect a sequence like this at the beginning of this course, I think that you would have found that to be really challenging. But I believe that we will be able to do this without too much difficulty now that we have learned all the things that we have done, that we've learned in this course. Now, one more word before we go ahead and jump into this problem. Why did I choose this particular sequence? And the reason that I chose this sequence is that, okay, we're looking here at a sequence of length 3. It has 3 bits in it. And so we know that there are 8 total sequences of 3 bits. There's 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Now, if you look, you will see, if you look carefully, you will see that all of these sequences are present in the X sequence shown. For instance, it's obvious here that 0, 0, 0 is right there. And 0, 0, 1 is right here. 0, 1, 0 is right there. 0, 1, 1 is right there. 1, 0, 0 is right here. 1, 0, 1 is right there. 1, 1, 0 is right here. It occurs elsewhere as well, but I just want to make sure we have at least one instance of every sequence. And 1, 1, 1 is right here. So this way we will get to test out our machine on all the possible sequences of length 3. And what we hope is that this machine will always output a 0, except when the present input and the 2 immediately preceding inputs are 0, 1, 1. So that's what we have. Okay, well, we're going to start with the state diagram for this problem and work our way sort of like backwards. If you want to think of an analysis problem, we will work back until we get the actual components of the system, and we'll have a diagram for our synchronous state machine. So let's see how this will go. Okay, I'm going to define some states first. And let me just make one thing clear. The part of this problem that is similar to problem 32.3 will be at the very end of this video. So if you're if you're not really interested in seeing the background and you just want to see that, then you can skip to the end of this video. But I don't think it's going to be a very long video, and I hope that it will help to sort of tie everything together. So I hope that you'll want to go ahead and stick with it. So we'll have states that we will call S0, S1, S2, and S3, and this just means last two inputs are 0, 0. This is the last two inputs are 0, 1. This is the last two inputs are 1, 0. And this is the last two inputs are 1, 1. Okay, so let's think about it for a moment. Here we'll have S0, S1, S2, and S3. So suppose that you are in S0 and you get an input of 0. Where do you go? Well, you stay right in S0, because it will still be the case then that the last two inputs are 0, and since then that will mean that the last three, or the previous two inputs and the present input, are the sequence 0, 0, 0, and that's not your desired sequence, so you're going to output 0 as well. So if you input 0, you go back to the same state and output 0. On the other hand, if you get a 1, then that means that the last two inputs have been 0, 1, so that means you want to go to S1. And that also means then that the present input and the previous two form the sequence 0, 0, 1, which is not your desired sequence, so we will output a 0. Okay, now let's go to state 1, which means that the last two inputs are 0, 1. Okay, well, if you input a 0 and you're in state S1, then that means that the last two inputs will be 1, 0, which is state 2. So that's what happens. That's where we go if the input is 0. And the last three, the present input and the two immediately preceding ones in that case would be 0, 1, 0, which does not match your desired sequence, so you output 0. On the other hand, if you are in state S1 and your input is 1, then the last two inputs will be 1, 1. So you will go down to S3 in that case. And and also you can say that if the present input is 1, and then you're in state S1, which means the two previous ones were 0, 1, then the last three altogether are 0, 1, 1, which is indeed the desired sequence. So here we will output a 1. Now let's go to S2, which means that the last two inputs have been 1, 0. Well, if you're in that state and you get a 0, then the last two will be 0, 0, which will take you back to S0. So we have a 0. And then in that case, the last three inputs are 1, 0, 0, which does not match your desired sequence, so we output 0. And on the other hand, if you are in S2 and the input is 1, then the last two inputs will be 0, 1, which would be back up to state 1. This is 1. And the last three inputs in that case would be 1, 0, 1, which does not match your desired sequence, so you output a 0. And finally, if we are in the state S3, which is 1, 1, and we get an input of 0, that will take us to S2, 1, 0. That's 0. And in that case, the last three inputs then are 1, 1, 0, which does not match the desired sequence. So we output 0. And finally, if we are in state 3, 1, 1, and we get a input of 1, then we go back to state 3, and we will output a 0 because the last three inputs are 1, 1, 1, and that is not our desired sequence. So you notice that there's altogether 8 arrows, and only one of them has an output of 1, that's exactly what we want, because we only want to output a 1 when we detect the desired sequence, and at all other times we want to output a 0. So this is, again, this is what we call the state diagram. And then the state table is just the same information, really, but just put in a tabular form. So we can say present state, next state, and by the way, we have not talked much about the state diagram or state table. We've talked about the state diagram a little, but we haven't talked about the state table too much. And the reason is that the state diagram, the state table, and the transition diagram, which we've talked about a lot, they all contain the same information, basically. So that's why we haven't really spent a whole lot of time talking about those topics. We've mainly talked about the transition diagram. Okay, so to summarize what we have, if you're in S0 and the input is 0, then the next state is S0. On the other hand, if you're in S0 and the input is 1, well, I might as well go ahead and put the output too. So if you're in S0 and the input is 0, then you go to S0 and you output 0. And all of that is from right there. Okay? On the other hand, if you're in S0 and the input is 1, then you go to S1 and you output, oops, should be up here. Let's see. Now we have it right. Okay. And so if you're in S0 and the input is 1, then you go to S1 and you output a 0. If you're in S1 and the input is 0, you go to S2 and output is 0. But if you're in S1 and the input is 1, you go to S3 and output a 1. Okay, if you're in S2 and the input is 0, you go to S0 and output is 0. But if you're in S2 and the input is 1, you go to S1 and output a 0. Finally, if you're in S3 and the input is 0, you go to S2 and output is 0. But if you're in S3 and your input is 1, you go back to S3 and output is 0. So those, that is our state table. And now, if we assign, if we say that S0 corresponds to A equals 0 and B equals 0, S1 corresponds to A equals 0, B equals 1, S2 is A equals 1, B equals 0, and S3 is A equals 1, B equals 1. Then what we have for our transition table will be the following. He moved up one line there. Okay, so now we're ready to fill in the transition table. And of course, this is really simple. Okay, so S0 corresponds to 0, 0. S1 corresponds to 0, 1. S2 corresponds to 1, 0. S3 corresponds to 1, 1. S0 corresponds to 0, 0. S1 corresponds to 0, 1. S2 corresponds to 1, 0. And finally, S3 is 1, 1. And here we have 0, 0, 0, 0, and 0, 1, 0, 0. So that was very easy. And again, that's what I'm saying, is that the transition table really essentially has the same information as the state table, which really has the same information as the state diagram. But still, it's nice to see it in different ways, and nice to have some familiarity with all of these. But the transition table is what we are really familiar with. And so now we have what people call a design decision. And our design decision is the following. What we have to decide here is how are we going to make these transitions occur. I mean, this transition table is telling us how the present value of A transitions to the next value of A, and the present value of B transitions to the next value of B. But what causes these transitions? Well, you have a decision. What kind of flip-flops do you want to use? And we have talked extensively about 3 different kinds: the T flip-flop, the D flip-flop, and the JK flip-flop. And as I have said before, you don't have to use the same kind of flip-flop for A as you do for B. And so just to illustrate that point, and also to give us more practice, what I will do is I'll use a JK flip-flop for A. So I'll have JA, KA. But for B, I will use a T flip-flop. And so we now need to create our excitation table to find out what all of those are. And remember, this is I think the most difficult, for sure, the most difficult part of this procedure. Okay, so we have A and B, and then we'll have JA, KA for x equals 0 and x equals 1. And then we'll have TB for x equals 0 and x equals 1. And then we will have Z for x equals 0 and x equals 1. Okay. And once we get this straight, we're in the home stretch. Okay. So remember now that in this transition table, the first values here are representing the next values of A. And of course, this column is the present value of A. So if we have a JK flip-flop, and I'm looking first in the x equals 0 column, if we have a JK flip-flop and A goes from 0 to 0, then that means JAKA is either 0, 0 or 0, 1. So that's 0, 0, D. The next transition is 0 to 1, and that could be caused by either 1, 0 or 1, 1. And so that's 1, D. The next transition is from 1 to 0, which could be caused by 1, 1 or 0, 1. So we have D1. And in the final row, we have 1 going to 1, which could be 0, 0 or 1, 0. So that's D0. Now let's look at the x equals 1 column. Actually, if you look carefully, you will see that the x equals 1 column, that the next values of a are always the next values of a in these two columns are actually the same. So we can say that JAKA will be the same when x is equal to 1 as it is when x is equal to 0. So again, we will have 0, D, 1, D, D, 1, D, 0. Okay, so now we're ready to look at B. So here's the present values of B, and here's the next values of B when x is equal to 0, and here are the next values of B when x is equal to 1. And so let's see how this will go then. Remember now that we have TB. Okay, so going first down the x equals 0 column, we have 0 going to 0. And the value of TB that will make that happen is 0. Next, we have 1 going to 0, so TB is 1. Next, we have 0 going to 0, so TB is 0. And then we have 1 going to 0, so TB is 1. Now let's go down to x equals 1 column. 0 going to 1 means TB is 1. 1 going to 1 means TB is 0. 0 going to 1 means TB is 1. And 1 going to 1 means TB is 0. And then the z's just stay the same. Okay. So now we are ready. Now that we have found out what our excitations should be, what we now want to do is to find minimal sums for each of these so that we can have circuits that are as simple as possible. So we're going to have to do Carnot maps for JA, KA, TB, and Z. Okay. So let's look at JA. Okay, now going x equals 0, this is JA when x is equal to 0, and this is JA when x is equal to 1. So if we fill in then, we will have in the x equals 0 row, we have 0, 1, skip over, D, and then D. And then in the x equals 1 column, it's exactly the same. 0, 1, skip over, D, and then come back, D. Okay, that's the Carnot map for JA. Now I think I'm going to go ahead and fill in the Carnot map for KA and TB and Z. I'll get all the Carnot maps, and then we'll do the analysis. So the next Carnot map now will be KA. And then we're going to have one for TB. And then finally we'll have one for Z. Okay. So now filling in for KA, we will have D, D, 1, 0, and again, D, D, 1, 0. That's for KA. And then for TB, we will have 0, 1, skip over, 0, 1. And for x equals 1 row, we will have 1, 0, skip 1, and come back 0. And then finally for Z, we just have all zeros in the top row, and in the bottom row, 0, 1, 0, 0, like that. And now, in keeping with what I've been doing lately in class, I will replace all the blue D's with red 1s. Those are the don't care conditions. So now we have that, and now we're ready to do our analysis. So for JA, when we look at the prime implicants, we have two groupings of 4. We have a grouping of 4 right here in the middle, which is just B, and then we have a grouping of 4 in the right half. So in other words, this one, and the first one is this one, and that second one is A. And since the don't care conditions can never be essential, the only essential prime implicant is B. And if we look then at minimal sums, we see that JA is equal to, remember, we have to start with what's essential, so JA is equal to B, and then if you shade in that, and then ask yourself if you have accounted for everything that needs to be accounted for, the answer is yes, because you don't have to account for the red stuff, that's don't care, and so we're done. And so here we have JA is equal to B, which obviously is going to be very simple in terms of our circuit. Okay, now let's look at KA. Okay, so again, we'll look at prime implicants. And once again, we have two groupings of 4. We have this grouping of 4 that is right there, like this. And that grouping of 4 will be B prime. And then there is another grouping of 4, like this. And that is A prime. The essential prime implicants only, let me circle the one for A prime here. It's this one. But only B prime is essential, once again, because don't care conditions can never be essential. And so the minimal sums here will be KA is equal to B prime. And then if we shade in B prime and ask ourselves, have we accounted for everything that has to be accounted for? And the answer is yes. So there's KA. Okay, now the remaining two kernel maps are not quite as simple, but they're still not bad. For TB, you can see that we have two prime implicants of size 2. And so let's that. And the first one there will be x prime, and b, x prime b. And then the second one will be x b prime. And both of those are essential and the minimal sum then is TB equals x prime b or x b prime. And you might notice that that is x exclusive ORed with b, but I'll just leave it like that for right now. Okay, and then finally for z, it only has one cell, so you can immediately see then that z is just equal to x a prime b. Okay, so now if we have done everything correctly, we should be able to draw our drawing. So let's see how this will go. We will have a JK flip-flop. Here's JA, KA. And I'm not going to be showing the clock signals in these diagrams because I think that will just clutter it up a bit, so we won't be showing the clocks. And then we have TB, okay, and now let's see what we can do with this. Okay, JA is equal to B, so we have that. And KA is equal to B prime. And so we have that. And TB is equal to X prime B or XB prime. So let's see how we can do this. We'll have an OR gate. And what is getting ORed together is, let's see here. Maybe I need to move all this over a little bit. Okay, so let's say that we have over here to the left, we'll have X. Okay, now see if you agree with that. Let's look carefully and I'll try to explain it. Okay, here we have X right here. And so right here we will have X prime. And notice that X prime and B are getting ANDed together right there. On the other hand, right here we have X, and here on this line we have B prime. So here will be X B prime, and that's going to get ORed together with the X prime B. And so that will give us TB. Okay, and now the last thing we need to do is to form Z. And Z is equal to X ANDed with B and A prime. And there we have our synchronous state machine. And our claim is that this will detect the sequence up here, the 0, 1, 1. So now is our chance to check that. And so now we go back in the other direction. Okay, remember that if you have a synchronous state machine like this and you want to analyze it, the first thing you do is get the excitation equations. And so we'll do that. Let's see. We have JA, KA, TB, and we also have the output equation for Z. Okay, and now if we look at this diagram, it looks like JA is equal to B, and KA is equal to B prime. The only one that's complicated is TB, and let's see, TB is two things getting ORed together, and the things that are getting ORed together are B with X prime, so we have B X prime, and that's getting ORed with B prime ANDed with X. And then finally, Z is equal to X, B, A prime. So those four equations actually have all the information we need for this synchronous state machine. And so let's now have our excitation table. So we'll have A, B, JA, KA, when X is equal to 0, and when X is equal to 1. And then we'll have TB, when X is equal to 0, and X is equal to 1. And Z, when X is equal to 0, and X is equal to 1. Okay, so for JA is real easy because it's just equal to B. So it'll be 0, 1, 0, 1, 0, 1, 0, 1. That's JA. And KA is just B prime. So we have 1, 0, 1, 0, 1, 0, 1, 0. So JAKA is very easy. Now let's look at TB. It's BX prime or B prime X. Okay, so when X is equal to 0, in the X equals 0 column, the second term drops out, and the first term just becomes B ANDed with 0 prime, which is B ANDed with 1 or B. So TB is just equal to B in the x equals 0 column, which is 0, 1, 0, 1. And on the other hand, when x is equal to 1, the first term will drop out, and we're just left with the second term, b prime ended with x, which is 1, so b prime ended with 1, which is b prime. So we get 1, 0, 1, 0. And then finally for z, well, when in the x equals 0 column, we get all zeros because of the x that we see in z. So 0, 0, 0, 0. And on the other hand, when x is equal to 1, z is equal to b a prime, which will be equal to 1 when a is 0 and b is 1, but it will be equal to 0 in all the other cases. So there is our excitation table. Okay, so now we want to look at that to get the transition table. Okay. So, to determine the next value of A, we need to look at JAKA. So going down the x equals 0 column, okay, if A is 0 and JAKA is 0, 1, then the next value of A will be 0. And actually, well, I guess just go one at a time. If A is 0 and JAKA is 1, 0, then we get a 1. If A is 1 and JAKA is 0, 1, then we go to 0. And finally, if A is 1 and JAKA is 1, 0, we go to 1. And the values of JAKA are all the same in the x equal 1 column as they are in the x equals 0 column, so we're going to get the same answers right here. Now, what about for B? Okay, going down the x equals 0 column for TB, and remembering how T flip-flops work, okay, if the current value of B is 0 and TB is 0, then the next value of B will also be 0. Okay, if B is 1 and TB is 1, then the next value of B will be 0. If B is 0 and TB is 0, then the next value of B will be 0. And finally, if B is 1 and TB is 1, then the next value of B will be 0. Now going down the x equals 1 column, if B is 0 and TB is 1, then the next value of B will be 1. If B is 1 and TB is 0, the next value of B will be 1. If B is 0 and TB is 1, the next value of B will be 1. And finally, if B is 1 and TB is 0, the next value of B will be 1. And then we just copy down the values for Z. Okay. And now we are ready to finish this problem. So let's bring down this sequence that we have up here. And now this is the part that is like problem 32.3. Okay. So the way that I suggest that you do problems like this is the following. Okay, you will have A and B up here. And you write your X sequence. And now you need to know something about an initial state in problems like this. And in 32.3, you are given information that the initial state is A equals 0 and B is equal to 0, and that's almost always where we will start. So that's what we'll do in this case as well. We will start with 0, 0. So A is 0 and B is 0, and we get X equals 0. So what happens? Okay, now according to this transition table, see, we have to look at the transition table to see what happens. If we are in 0, 0, and X is equal to 0, 0, then we will go to 0, 0 and output a 0. So the next AB will be 0, 0. And our current output will be 0. Now in the next column, we have exactly the same situation. We're in 0, 0, and we get a 0. And so once again, our next values of AB will be 0, 0, and our present output will be 0. And then once again, we have that situation. So again, 0, 0, and we output a 0. But now, in this next one, is finally going to be something different. We're in 0, 0. You see, we're in 0, 0. A is 0 and B is 0. But now we get a 1. So if we're in 0, 0 and we get a 1, where do we go? We go to 0, 1 and output a 0. So now I'm going to say, let me erase these circles. So now we're going to go to 0, 1. Oh, let's see. And we're going to output a 0. And actually, let me see if I can sort of accomplish this. Spread those apart. It makes it a little easier to see. Now, in this next case is where it gets really interesting, because we are in 0, 1, and we get an input of 1. So what happens in that case? Okay. We're in 0, 1, and we have an input of 1. So where do we go? We go to 1, 1, and we output a 1. So let me put that. 1, 1 is where we're going to go next, and our current output will be 1. Okay. Now, now we're in 1, 1, and we get a 1. You see, we're in 1, 1, and we get a 1. Let me erase these others. There, we're in 1, 1, and we get a 1. Where do we go? We go to, so here's 1, we're in 1, 1, oops. Yeah, we're in 1, 1, and we get a 1. So we go to 1, 1, and output a 0. So we go to 1, 1, and we output a 0. Let me make that blue. Not that it matters too much. So go to 1, 1, and output a 0. Okay. We're almost done. Now we're in 1, 1, and we get a 0. So you can see we go to 1, 0, and output a 0. Go to 1, 0, output a 0. Now we're in 1, 0, and we get a 1. So here's 1, 0, and we get a 1, so we got a 0, 1, and output a 0, 0, 1, and output a 0. And then we're in 0, 1, and we input a 0, so we're in 0, 1, and we have input of 0, so we're going to go to 1, 0, and output a 0. Go to 1, 0, output a 0. Okay, now we're in 1, 0, and get a 0. So we're in 1, 0, and we get a 0, so we go to 0, 0, and output a 0, 0, 0, and output a 0. Okay, now we're in 0, 0, and we get a 1, so we're in 0, 0, and get a 1, so we go to 0, 1, and output a 0, 0, 1, and output a 0. Now we're in 0, 1, and we have an input of 0, so we're in 0, 1, and input of 0 means we go to 1, 0, and output a 0, 1, 0, output a 0. Okay, now we are in 1, 0, and we get a 1, so 1, 0, and we get a 1, so we go to 0, 1, output a 0, 0, 1, output a 0. And now we're in 0, 1, and we get a 1, so we're in 0, 1, and we get a 1, so we go to 1, 1, and output a 1. So go to 1, 1, and output a 1. And finally, we're in 1, 1, and get a 0. We're in 1, 1, and get a 0, so we go to 1, 0, and output a 0. Go to 1, 0, output a 0. And we are now done. And I ask you to look at these last two lines. And is this machine acting properly? And you can see that sure enough, it is. Because it has output a 1 on 2 occasions. And in both of those times, see, right here, it outputs a 1. And you can see that that corresponds to the present input is 1, and the previous 2 were 0, 1. And likewise, right here, we output a 1. And that corresponds again to the present input is 1, and the previous 2 were 0, 1. But at all other times, the output is 0 because we don't have that sequence any other time. So there you have it. And I really do hope that that impresses you with what you can do, because, you know, to me, that's just really neat that with the things we've learned in this course, we're able to find out exactly how to build this sequence detector. And as I say, this very last part is the part that is like problem 3 on test 32. So I think that should fully prepare you for test 32. And so good luck and have a great weekend.